Hello everyone, I'm Norman Wildberger and welcome to 6, an elementary course in pure mathematics. So we've been talking about the bridge between 3 and 4. That's kind of on our way to understanding 6 things. And it will turn out that there's another bridge between two numbers, a little bit bigger, that will also play a very important role. So we want to understand this 3-4 bridge quite well, and this is really nice because it connects with a lot of other actually important things in mathematics. And today we're going to talk about connections with geometry, in particular triangle geometry, and we're going to see connections between the classical incenters and orthocenters and this 3-4 bridge. So let me remind you, we start with 4 points, say 1, 2, 3, 4 in the plane, and then we create these diagonal points where opposite lines or edges meet, and we get the points A, B, C forming the diagonal triangle. So we are going from 4 points to 3 points. All right. Now, I should maybe say this is the diagram that I usually make for this, but it's probably important to realize that these 4 points that we start with don't have to form a convex quadrilateral. Okay, so it's, in other words, possible for one of the points to be inside the triangle formed by the other 3. So perhaps you might like to draw a corresponding picture like that, where, say, the point 4 is moved from out here to, say, being inside the triangle 1, 2, 3. Everything still works. We just get a different looking configuration. Now, the question that we want to address today is, how do we go in the other direction on this bridge? If we start with 3 things, like, say, the triangle ABC in the plane, how can we go back to a quadrilateral or quadrangle of 4 points so that we still have this relationship? Now, there's a bit of an asymmetry here because 4 is bigger than 3. And although it's reasonable to go from 4 points to 3 points uniquely, like in this situation here, it's not so obvious that we should be able to go backwards uniquely. In other words, we can't really expect that given 3 points, there's a unique configuration of 4 general points that are somehow determined by them. Okay, so that's a bit of an aspect here. 4 to 3, we're losing some information and we can't recover it so quickly. Anyway, but answering this question is quite interesting and connects with some interesting triangle geometry. Triangle geometry is the study of this very elementary configuration, just 3 points, A, B, C, and the 3 lines in the plane that they form. It's an aspect of geometry that goes back to the ancient Greeks, who discovered and investigated the 4 simplest triangle centers: the incenter, the centroid, the circumcenter, and the orthocenter. So these go back thousands of years. But in more modern times, in European times, a lot more additional triangle centers have been discovered. First hundreds and then thousands of them. And so now it's an incredibly rich topic, perhaps the richest branch of mathematics, actually. So let's talk about the triangle center, the incenter, first. Actually, that's the first one on Clark Kimberling's famous list. So he has a website called Encyclopedia of Triangle Centers, which lists thousands of triangle centers. And the incenter is actually the very first one on his list. So this is a great resource for people interested in geometry, and I encourage you to have a look at it. So how do we get the incenter? Well, there it is there for this triangle here. It's the point that has the property that you can inscribe a circle in the triangle with center at that point I. So that's the center of this circle here, which is inscribed in the triangle, meaning that it's tangent to the 3 sides of the triangle. To construct it classically, one looks at so-called angle bisectors, which I prefer to call bylines. So for example, at A, this is an angle bisector or a byline. Traditionally, it means that this angle here and this angle here are the same. In rational trigonometry, we prefer to think about spreads, which are more algebraic and computational than angles. So the corresponding statement would be that this spread is the same as this spread. Okay, and then there's a corresponding angle bisector or byline at B and another one at C. And lo and behold, these three intersect at this point I. And that's the incenter, and that's the very first point on Clark Kimberling's list of triangle centers. Euclid's famous book, The Elements, is very interested in constructions, geometrical constructions, and constructions of angle bisectors or bylines, figures prominently even in Book 1. In Proposition 9, he shows how to construct bisectors or bylines when you have two lines meeting at a point A. He says what you should do is you should draw a circle centered at A and see where it meets the two lines in question. And then you connect those 2 points with a line like this. And then you actually use Proposition 1 of Book 1, which shows how to construct an equilateral triangle on this base. Okay, so what you do is you get your compass and you put the center here and you draw a circle through the other point. So something like this. Okay, that's supposed to be a circle around this point here. And then you move the compass to this point here and you draw a circle with center here through the other point. Okay, that's some other thing, some other circle like this. All right, and then where those two circles meet, well, they actually meet in 2 different places, but say that would be one of them there. Okay, and then you connect these points there, and that's then an equilateral triangle. So that's the very first proposition of Book 1. Of course, then if you can do that, well, then you can join this new point that we're creating here with the original vertex A, and then you get an angle bisector so that that spread is the same as that spread. Or if you're talking about angles, the angles are equal. As far as Euclid would have stated it, he would have said, well, this angle is equal to that angle in the following sense, that this geometrical configuration is the same as this geometrical configuration in terms of picking this up and putting it down over there. So he does not actually talk about angle measurement. Okay, he talks about angles as geometrical objects that can be moved and superimposed on each other. Okay. But in any case, that's how the classical story of angle bisectors is usually explained. Now, actually, when we go to a more algebraic, modern point of view, we see that the situation is a little bit more subtle and actually involves some number theoretic considerations which are maybe not so obvious when you're just drawing on a piece of paper. So the real story is more like this. You have a point there, let's call it A as well. And you have these 2 lines meeting at A. But actually the lines go off in different directions, right? They're not just necessarily rays. So how do we form angle bisectors for this configuration? Well, we still use the circle centered at A and see where it meets, say, the 2 lines. So we could, use that point, and then we could do the construction that we've just done and get this equilateral triangle there. And then we could say, aha, now we have an angle bisector. Fine. But actually, when you're drawing the circle, there's some choices involved because this circle meets one of these lines, if it does at all, in 2 points typically. So we could also have chosen, say, this point here and this point over here. Okay, if we had done it that way, then the equilateral triangle that we would form would be up here somewhere like this. And then when we join with A, we would get this as an angle bisector. Okay, so actually, if you do this sort of more general thing and look at all the possibilities, you get 2 angle bisectors, and crucially, they are perpendicular. Okay, so I might write that there. So there are 2 bylines, and they are perpendicular. So that's interesting. That allows us to think about incenters in a broader, actually better way. Okay, so let's return to that initial picture that I showed you of the incenter, and let's look at it a little bit in a broader setting. Okay, so here's a triangle ABC, okay, and when we are constructing angle bisectors or bylines now, we see that they come in pairs. So that's the first one that we saw, but there's actually this other one, which is in some sense algebraically just as valid a solution to what's ultimately a kind of a quadratic equation if you write down the algebra for it. So we have these two bylines which are actually perpendicular at A. We have these two bylines which are actually perpendicular at B. And we have these two bylines which are actually perpendicular at C. So starting with the triangle ABC, we actually have 6 bylines. Okay, that makes us happy because we like 6. All right. And then these 6 bylines meet in various places. They meet, at least 3 of them meet at this first incenter that we've already discussed, which is the center of this circle inscribed in the triangle. But also, the other ones also meet in 3 additional points. So this byline and this byline and this byline meet in I2, and these 3 here meet in I3, and these 3 here meet in I4. And these other incenters, sometimes they're called excenters, but it's really better to think of them as all being incenters. Okay? They are also sharing the property that they are the centers of circles which are tangent to the original sides of the triangle, as you can see here. So I2 is the center of this circle, which is still tangent to the 3 sides of the triangle. I3 is the center of this big circle here. I4 is the center of this circle here. So you see that what we're doing is we're crossing this 3-4 bridge because we're starting with a triangle and we're making a construction that ends up with 4 incenters. So we get this quadrangle, I1, I2, I3, I4. And if we look at the diagonal triangle of that, how do we get that? Well, we just join these various 4 points in all 6 possible ways and see what the new points of intersection are. Well, this edge and this edge will meet in C. This edge and this edge will meet in B. This edge and this edge will meet in A. So ABC is the diagonal triangle for this in-center quadrangle. So we're going now from 3 to 4, and this is reversing the pattern that we saw originally, going from 4 to 3. So now we can cross the 3-4 bridge in either direction. Now I want to talk a little bit about the orthocenter. That's another famous triangle center, which usually is quite separate in some sense from the in-center story, but we'll see that there's actually a very interesting connection having to do with this 3-4 bridge. So if you have a triangle, say ABC, then the orthocenter is the meet of the altitudes. So an altitude is a line through a vertex like this one here, which is perpendicular to the opposite side, side BC. So that's an altitude. The altitude through B is this line here. It's perpendicular to AC. And the altitude through C is this line here. It's perpendicular to AB. And as you can see here, these 3 altitudes meet at a point D. The fact that these 3 altitudes meet is actually quite non-trivial. And folklore has it that it was Albert Einstein's favorite theorem in elementary geometry. It is a very nice fact. But when we look at this picture, so D is the orthocenter of triangle ABC, we actually see that there's more symmetry around. And we're interested in symmetry. We also see that, in fact, the same diagram shows that the point A is actually the orthocenter of the triangle BCD. Let's think about that, okay? So if we had started with this triangle BCD, what are the altitudes of it? Well, suppose that we're looking at the altitude from D to the opposite side. So that would be this line here. What about the altitude from B to the opposite side? The opposite side is CD. Well, the altitude line is going to be this line right here. So that's an altitude. And what about the altitude from C to this opposite side? That's going to be this line here. So the 3 altitudes of the triangle BCD are this line, and this line, and lo and behold, they do meet at the point A. So A is the orthocenter of the triangle BCD. And similarly, B is the orthocenter of the triangle ACD. And C, this one here, is the orthocenter of the triangle ABD. So when we just look at a diagram like this, we actually can see 4 different orthocenters of 4 different triangles. These 4 points A, B, C, D have a very pleasant kind of 4-fold symmetry. And we say that they are an orthocentric quadrangle. So ABCD is an orthocentric quadrangle. Any one of those 4 points is the orthocenter of the other 3. Now, associated with this orthocentric quadrangle, ABCD, is this triangle EFG. What's that? That is a triangle formed by the feet of the altitudes. So if we go back to the original triangle ABC, and then we looked at the altitudes here, the feet of the altitudes, the places where those altitudes meet the opposite sides, are the points E, F, and G. So that triangle is the feet of the altitudes, called the orthic triangle of ABC. But it's easy to see, just from the kind of thing I've been saying, that it's also the orthic triangle of ABD, or of BCD, or of ACD. So this is a kind of common orthic triangle to all of the triangles formed in this orthocentric quadrangle. So it's a kind of another 3-4 connection, right? We've got these 4 points, A, B, C, D, forming this very special quadrangle. And then this triangle EFG, which is somehow beautifully associated to the quadrangle, going from 4 to 3. Okay, so now I can tell you a magical fact. Something which is not obvious. Something which you look at and say, wow, that's cool. And that's typical of the beauty of triangle geometry. It's that these 2 diagrams I've shown you, these 2 pictures of the in-center story of a triangle and these orthocentric quadrangles, they are really, in some sense, the same picture. Okay, so let me show you. So here's the sort of the first picture that I started with. We started with the triangle ABC, and we were looking at incenters formed by bylines at the various vertices. Okay, and we had these 4 incenters: I1, I2, I3, I4. Now, if we just look at this quadrangle, I1, I2, I3, I4, that should be A1. Okay, let's make it a 1. Okay. That thing is actually an orthocentric quadrangle. And its orthic triangle is the original triangle ABC. So what makes it an orthocentric quadrangle? Well, any one of these incenters is actually the orthocenter of the triangle formed by the other 3 incenters. So for example, this I1 here is actually the orthocenter of the triangle I2, I3, I4. And that's kind of obvious because we know that these bylines are perpendicular. So this is a byline at B, and this is a byline at B. So yes, indeed, this line here is really the altitude from I3 to I2, I4. This is an altitude from I2 to I3, I4. And this one here is an altitude from I4 to I2, I3. So yes, indeed, I1 is actually the orthocenter of I2, I3, I4. And then from that symmetry that we've already observed, that means that this is an orthocentric quadrangle, and similarly, I2 is the orthocenter of I3, I4, I1, etc. So we can see the orthocentric quadrangle picture in the in-center story. But conversely, if we go starting with the orthocentric quadrangle story, so here's a copy of that orthocenter diagram. We started with A, B, C, and we drew altitudes, and we found D to be the orthocenter of the triangle ABC, and then we said, okay, now we actually have an orthocentric quadrangle ABCD with orthic triangle EFG. What I'm claiming now is that this diagram here is actually really the same as an incenter diagram. Namely, ABCD, this is actually the quadrangle of incenters of DEF. This triangle DEF here, this orthic triangle, its incenters are exactly D, A, B, and C. That's a non-trivial fact. It's not so easy to prove. If you have some experience in geometry, you might like to try to prove that. But for your homework, I don't want you to prove it. I want you to verify it. So I'm making statements here. I want you to open up GeoGebra and test this out and see, is this really true? So if we start with a triangle ABC and we construct its orthocenter and then construct this orthic triangle here, is it really true that these things are incenters? In other words, is this really a byline or an angle bisector of the triangle EFG? You can verify that using GeoGebra. Okay? So that'll make you confident that yes, these statements are probably true, even if they do have a kind of a magical aspect. All right, so in today's lecture, we've shown that this 3-4 bridge actually has a manifestation in the world of triangle geometry, and it connects naturally with the 4 incenters of a triangle, and it connects with the orthocentric quadrangle that we get by looking at orthocenters of a triangle, and that these stories are, in some sense, really the same. So this 3-4 bridge is quite rich. I'm Norman Wildberger. Thanks for listening.